In 01 knapsack problem part 1 we described 01 knapsack problem, and with examples I explained that 01 knapsack problem cannot be solved using greedy technique, and this is more difficult as compared to the simple knapsack or fractional knapsack that can be solved using greedy technique. So and today we will discuss backtracking algorithm to solve 01 knapsack problem. Okay, so as we know that to solve any problem using backtracking, just what first we define its explicit constraints and implicit constraints. Okay, so here first the what problems we have solved already with backtracking are, see, the first one is n queen problem, and the second is sum of subset problem, sum of subset problem, and the third is graph coloring problem, and Hamiltonian cycle. So these are the problems what we have already solved using backtracking algorithm. Okay, now we are going to solve 01 knapsack problem. See here in n queen problem, sum of subset problem, graph coloring and Hamiltonian cycles, they all, in all the problems there are number of solutions. Like n queen problem, there can be the more than one solutions to place the queen. The same in the sum of subset, there can be the number of subset whose sum equal to m. Graph coloring problem, if m is given and the graph is given, there can be the number of ways to color the graph so that no two vertices are of same color, no two adjacent vertices are of same color. Same in Hamiltonian cycle, there can be the more number of cycles exist in a particular graph. But in 01 knapsack problem, there is only one solution whose profit is maximum. So see the difference in the 01 knapsack problem and all the previous problems what we have solved using backtracking algorithm. So backtracking algorithm can be used to solve problems that have number of solutions, or it can be used to solve optimization problem where our objective is to find one optimal solution. That is the case of 01 knapsack problem. Okay, so here in the 01 knapsack problem, simply just our objective is to generate one optimal solution, but the approach is same. Here first we conceive the state space tree, and the solution space can be formulated in two ways, either variable size tuple like in the sum of subset, or fixed size tuple. So here the solution space can be formulated in two ways, either variable size tuple or fixed size tuple, as in the case of sum of subset problem. Like if suppose our profit vector n is equal to 3, what example I have taken in the part 1, n equal to 3, m equal to 50, and p equal to say 60, 100, 120, and w is 10, 20 and 30. Okay, so suppose if we represent its solution using variable size tuple. So variable size tuple, simply we index the objects like 1, 2, 3. So here, so first we determine all feasible solutions. Okay, so for the all feasible solution, simply just we are not considering any object. I am not giving the optimal solution. The feasible solution is that we are not selecting any particular object in the knapsack. Okay. The second, we can select 1, or simply we can select 2, or we can select 3, because here the 10 can be selected because the knapsack capacity is 50. 2 can be selected, knapsack capacity 20 and 30. The same we can select 1, 2. Okay, in this way, or we can write 1 and 3. We can write 2, 3 and so on. Okay, so these are the various representation in these are the various solution vector when we use the variable tuple size. Okay, so if we use the variable tuple size, simply we use the index, but here we apply the backtracking solution with fixed tuple size. Okay, fixed tuple size means in the same problem n equal to 30, m equal to 50, n equal to 3, m equal to 50, and p is 60, 100, 120. Okay, so in the fixed tuple size, if we represent our selection vector in the fixed tuple size, then simply what I represented in the part 1, that its solution is what? The one feasible solution. Feasible solution means the knapsack capacity must not exceed from the sum of weight must not exceed from knapsack capacity. Okay, so this can be added 10, 1, 1 and 0. Okay, this is the one solution vector. For the second solution vector, here what? 1, 0, 1. This can be considered. The third solution vector is 1, 0, 0, and the another solution vector is what? 0, 0, 1 and so on. Okay, so there can be, so here in the if we represent the solution vector using fixed tuple size. Okay, so first thing, the size of the solution vector. Size of the solution vector is equal to the number of object, and every element of the solution vector can be either 0 or 1. Okay, so what if we represent the solution space by the fixed tuple size, then the explicit constraints here, in this case explicit constraints in 0-1 knapsack problem, explicit constraint that xi belongs to a set j such that j is an integer, xi belongs to what? 0, 1. Here the xi either can be 0 or 1 for every I greater than or equal to 1, less than or equal to n. This is the explicit constraints. Okay, now what is the implicit constraint? So just here the explicit constraint that all these tuple. Now the implicit constraint that simply there is a one tuple whose profit is maximum, and the back capacity should be the sum of weight should be less than or equal to back knapsack capacity. This is the implicit constraints. Okay, now first here when we generate the state space tree for 0-1 knapsack problem. Okay, just it is a difficult one, so just carefully listen carefully that here some bounding function is required, some upper bound is required to kill the node. Okay, so see, suppose if you are having the example like this example, what I discussed in the part 1, n equal to 4, m equal to 50, p equal to profit vector is this and weight vector is this one. Okay, here I am writing, suppose just n is 4. For this simply the state space tree consists of, say suppose, the three element. The first one is k. So we start that at this time solution vector is empty. So first we take the decision for what? First object, whether it is to be considered or not considered. Okay. And the second is weight of the knapsack. How much weight to be filled into the knapsack at present, and 0 is the profit. So always remember that this first component, this is k, this is the first, second represent weight, the current weight in the knapsack, and the third is the profit. Okay. So at present I am going to take the decision for the first object, and here as the no weight is in the knapsack, so the knapsack current weight is 0 and the current profit is also 0, as there is no weight or no object placed into the knapsack. So first we take the decision about first object. Okay. So see here, this I am writing here, n equal to 4 and m equal to 50, and then p is 54, 80, 72 and 120, and W equal to 6, 10, 12 and 30. Okay. So see here for this state space tree, always there are two ways. One, whether the particular object is included, and the left branch when the kth object is included, and the right branch the kth object is excluded. Okay. So here for the left branch, what will be the criteria? That simply just I will check the weight of first object, kth object, because we are taking the decision for the kth object, that is x1. Okay. So simply just one condition is sufficient, that if the weight of the kth object is less than or equal to knapsack capacity. So simply just here the one is required, that 6 is less than or equal to what? The knapsack capacity is 50. So here this x1 equal to 1, we can include the first object into the knapsack. So after adding the first object into the knapsack, what will be the situation? The recursively called what? K equal to 2, and now the weight in the knapsack is 6. Okay, as the first object is included into the knapsack, and because the first object is included in the knapsack, what profit is to be earned is 54. Okay. So now at present the knapsack filled knapsack is 6. Now the remaining, because the m is 50, m is here, the knapsack capacity is 50. So the remaining is what? The if we compare it with what is 6 is less than or equal to 50. This is the current weight. 6 is less than or equal to 50. So now we consider what? Another, just 10. Okay. So 10, simply 6 already added. So the next, I am going to take the decision for second object, and the weight of the second object W2 is here 10, and 10 plus 6 is 16. 16 is less than 50. So the second object can also be included. Okay. So here x2 equal to 1. Now after taking, just it will be updated, because now again the recursive call for the third object, and 6 plus 10, 16. Okay. So the current knapsack capacity is 16, and 54 as the second object I have included, and the profit of the second object, profit associated with the second object is 80. So simply 4 and 134, 54 plus 80. Second object's profit is 80. So 54 plus 80 is 4 and 134. Now for the fourth object. Fourth object, the weight is 12. So 12, 16, W3. W3 is 12. 16 plus 12 is what? 28, which is less than what? 50. So again, the third object can be included into the knapsack. Third object included. So now it will take the decision for the fourth object, and 16 plus 12, 28, and what will be the profit of the third object is 72. So here we add 72, 6 and this 206. Okay. So 206 is the current profit. Now see here, first object included. Now after that, the weight into the knapsack is 6 and the profit earned is 54. When the second object is also included, then the current weight in the knapsack is 16 and the profit earned is 134. Now the third object is included, the weight is 28 and the profit earned is 206. Now come to the fourth object. The fourth object's weight, see, W4 is what? 30. Okay, and here already 28 weight is added, so the knapsack capacity is 50. So if we add 30 and 28, it is what? Just 58. It is exceeding. So here the left branch is not feasible. Okay, so for the fourth object, left branch is not feasible. So here, whether to fourth object to consider or not, we will go for the right branch. Okay, so again see, for the left branch, one condition is sufficient, that whatever be the current object, what is the current weight filled into the knapsack plus the weight of the current object. Means if suppose I am saying that this is the current weight and this is the current profit, so simply one condition sufficient, that current weight plus WK should be less than or equal to M. Okay, so this condition is sufficient. If current weight and the weight of the kth object is less than or equal to M, then we can safely move to the left branch. Now here for the right branch, because there is some function required to kill the node, whether to move to the right branch or not. Okay, so here see, just because first thing, there is not a single solution, there can be the number of solutions, feasible solutions, but we have to find only one solution. So I don't know that this what 111, this is optimal solution, later on it will lead to the optimal solution or not. So initially we we store these vectors in some temporary variable, but just instead of x, here I will take another variable, say y. Okay, and when finally just we get the one solution, then y will be overwritten into the x. Reason is that because 0-1 knapsack problem is having number of solution, is having single solution instead of number of solutions. Okay, but all the leaf nodes, simply the leaf node, those leaf nodes for which this condition summation pi xi less than or equal to m are feasible, but only just we have to find one leaf node, wixi I is equal to 1 to n, where the sum of the xi's are 0 and sum of the xi's are 1. Okay, so here some bounding function is required to check whether to move in the right branch or not. So for this we have to maintain the sum global profit earned. So initially no solution vector is generated. So suppose the final profit of the optimal solution, I will initialize it with -1. As soon as we get the one solution vector, f will be updated. Okay, so F here, F is representing the profit of the current solution vector generated. Till now no solution vector is generated, so the F is initialized with -1. Okay, so y3, so here y4, if we take, so y4 equal to 0, because there are 4 objects only. Okay, so y4 equal to 0, and this one is what, 5, 28 and 206. Okay, and here it will terminate 28, 206. So one solution is what? So now just I will reach to the what? Here there is no recursion. I will reach to the leaf node. So one solution is generated. The first solution vector is 1, 1, 1 and 0. Okay, and its current weight is 28, and here the profit is 206. So one solution is generated. So here all yi's will be written into the xi's. This is so far one solution vector is generated. In this way we generate the number of solution vector, and as soon as we get any solution vector whose profit is greater than the previously generated solution vector, we update the previous solution vector. So at this time this is x and its profit is 206. Carefully note down that this f is 206. Okay, here f, writing in this way, this one solution vector is generated so far. X is equal to 1, 1, 1, 1, 1, 1 and 0, and its profit is what, 206. Remember that this is the global variable. Okay, now see here ki whether to move this branch or not. So see, if suppose just here I am taking y3 equal to 0. What about if the third weight is excluded? Okay, so simply just we have to take the decision for fourth object, and there is no change in the weight filled into the knapsack, and no change in the profit earned so far, as the third weight is excluded. Now the question is ki whether the fourth weight is to be added or not. In case whether we have to move to this right branch further or not, here certain bounding function is required. Now listen very carefully that if I have taken the decision for say k object, okay, and we are excluding the kth object, means here the value of k is what, 3. So we are excluding the third object, k equal to 3. Okay, and now the rest object is what, 4. There are simply 4, but 4 to n, k plus 1 to n. So for the objects, for all objects I, here we relax the condition xi from 0 or 1 to xi greater than or equal to 0, less than or equal to 1 for I equal to k plus 1 to n. Listen this condition, and this is the condition of bounding function for the right branch when I am excluding the kth object. So if you are excluding the kth object, so here some function is required, some bound is required whether to move in the right direction or not. Okay, so see what is the case, that here I will relax the condition for what, for I equal to k plus 1 to n, क्योंकि k तक तो ऑलरेडी डिसीजन ले लिया है, ठीक है, और kth ऑब्जेक्ट जो है वो एक्सक्लूड हो रहा है. अब k plus 1 से n पे जाने पे आपको क्या प्रॉफिट अर्न हो रहा है, ठीक है. सो हियर for this, for the objects from k plus 1 to n, the condition just 0 or 1 is relaxed. Here fractions are also allowed, and we solve the problem using greedy technique only for the objects from k plus 1 to n. As I have seen in the part 1 that greedy technique will always give you the maximum profit. Okay, so here see for the fourth object, the fourth object weight is what? 30. Fourth object weight is 30. W4 is 30, and here the remaining capacity, the capacity is 60 and the remaining capacity just m is 50, m equal to 50, and simply here the remaining capacity is if we say that the remaining capacity using R, then 50 minus 16. 50 minus 16 means 34. Okay, 34. This is the remaining capacity because 16 fill, and the weight is what? 30. Okay, so simply just we can add, because 16 plus 30, 46. So the last weight can be added. So here last weight can be, there is no need to take the fraction because the whole object is occupied, and simply just it is what for I k plus 1 to n, what we are getting the profit 134 plus 120. So now see the profit is the fourth object profit is, so total profit is 134 plus the profit of fourth object 134 plus 120, that is 254. So 254 is greater than the profit already generated solution vector. So we can go for right branch. Okay, so here see one solution, here there is only one solution vector is required. So for this solution vector, for this the solution vector generated so far, the output profit is 206, and if we go this branch, then the profit is 254. So what we do, just we go for here, and y4 equal to 1, and this is what? 5, and 16 plus what? 30 plus 16 is 46, and this is 254. So F is updated. Sorry, this is 206. Now see here, previously when I reached the leaf node 1110 and its profit is 206. Now I get more better solution, what? 1101. Okay, so then now y will again, this x will be overwritten by this. Now the new updated solution vector will be what? 1101, and its profit is 254. Okay, so what it is telling, that what solution vector generated so far, its profit is 254. Now here see this one. Okay, now again check the bounding function here, because for the left branch there is no need of bounding function, because only one condition is sufficient, that the weight included into the knapsack plus what? The current weight of the current object is less than or equal to m, we can move to the left branch. But for before moving right branch, just you have to find the bound, whether if we are moving in this direction and there is a possibility to get the solution vector whose profit is greater than 254. So we apply the same relaxation. Okay, so here carefully now see this one. Okay, so the y 2, y2 equal to 0. This is 3 and this is 6 and 54, as I have excluded the second object. Whether to move downward or not. Okay, so for this, from what I said, that here the value of k is 2. Okay, value of k is 2, where the second object is excluded. So for I equal to k plus 1 to n, here value of n is 4, 2 to 4. Relax the condition. Just relax the condition. You relax the condition like I. Relax the condition. Relax the condition xi equal to 0 or 1 to what? Xi greater than or equal to 0, less than or equal to 1. Fractions are allowed and we solve it with greedy method. Okay, so now carefully see, there is 6. At this time the weight filled, current weight is 6. Current weight is 6. Current profit is 54 and the k is 2. So k plus 1 to 4. K plus 1 is what? 3. Third object weight is 12. So 6 plus 12. Okay. So the 6 plus 12. The weight will be what? If we include the second object for what? For I equal to k plus 1 to n. So we add CW equal to what? 6 plus 12. That is 6 plus 12 is 18. Current weight is 18. And what will be the current profit? Current profit is 54. 54 plus 72. That is 126. This is for what? Second weight. कहाँ तक जाना है? K plus 1 to n. ठीक है? So again, just I equal to what? ये था I equal to 3 पे. ठीक है? I equal to 4. I equal to 4 पे CW क्या हो जाएगा? 18 plus 30. Now the 30 cannot be added. So I relax the condition कि just fractions are allowed. So just remaining capacity is what? R equal to 50 minus 18. 50 minus 18 is what? 32. Okay. So now the remaining capacity is 32. So here the weight is what? 30. So 30 can be added. So 30 can be added fully, because this is 18 plus 30 is 48, which is less than or equal to 50. So the current weight will be 18 plus 30, that is 48, and current profit is what? 126 plus 120. 126 plus 120, that is 6, 246. Now see, the profit is 246. Carefully see, the profit is 246 when we relax the condition. I am solving the condition. This is when we are applying the greedy technique, and already the solution is generated at 254. So it means कि just when we move down this tree, we will not get the better solution. What solution already generated so far means कि 3 से लेके 4 तक पे जो भी थे उस पर कंडीशन रिलैक्स करके मैंने ग्रीडी से प्रॉफिट निकाला. अगर वो प्रॉफिट जो अब तक सोल्यूशन वेक्टर जनरेटेड है उसके प्रॉफिट से ज़्यादा होगा तभी हम राइट ब्रांच पे मूव करेंगे, अदरवाइज राइट ब्रांच किल हो जाएगी. सो हियर आई विल नॉट एक्सप्लोर दिस node. I will not move further because just I have seen that from k plus 1 to 4 I am getting the solution vector whose profit is 246, which is less than the solution vector profit of the solution vector generated so far. So here this node is killed. Okay, so here no recursion is called. Okay. Now come to the main. This one. Here, this is what? X1 equal to 0. Y1, sorry. Y1 equal to 0. So here 2 and 0 and 0. Now, again, whether to move in this direction or not, some bounding function is required. Again, calculate. So here, what is the value of k? The value of k is 1, where the 1 is excluded. So अब कितने ऑब्जेक्ट हमारे बचे? 2 to n. ठीक है? तो जो i होगा वो i कहाँ से कहाँ तक लेना है आपको? k plus 1 to n. Here this is 2 to 4. ठीक है? So पहले i equal to 2 ले लेते हैं. ठीक है? i equal to 2. I equal to 2 का मतलब है कि second. So when I am taking the second one, the first one is excluded. ठीक है? तो second. So current weight अभी तो 0 है. 0 plus 10 equal to 10. Okay? Current profit अभी 0 है. 0 plus 80 is 80. ठीक है? Now I equal to 3. The current weight is 10 and the next weight is 12, which is less than or equal to 50. So I equal to 3. Current weight is 10 plus 12, that is 22, and current profit is 80 plus 72, that is 152. Okay. Now I equal to 4. Current weight 22 plus 30. Now 22 plus 30 is what? 22 plus 30 is 52. 52 is exceeding from the knapsack capacity 50. So here I will take the fraction. Why I am taking the fraction? To get the profit. If that profit is greater than to the profit for the vector generated so far, then only we consider this branch. We will explore this branch only. Okay. So I equal to 4. So here the CP. CW. So here the next I will take what? The remaining capacity. Compute the remaining capacity is what? The current capacity is 22 and 30. So 50 minus 22, that is what? 50 minus 22 is 28. Okay, so just the fraction part will be what part of this object to be considered. Simply CP equal to 152 plus 28 upon 30 into 120. Okay, so 0 0 cancel and 4. This is 152 plus 2 9 8 2 5 3 4 2 8 2. So this is what? 246 and 264. So here, if here I is equal to 2, second, third, फोर्थ वेट पे जस्ट जो है ये पूरा ऐड नहीं हो रहा है, तो मैंने क्या किया कि कंडीशन रिलैक्स कर दी. कंडीशन रिलैक्स करने पे क्या हुआ कि जो रिमेनिंग कैपेसिटी हुई 28 से प्रॉफिट कितना आएगा? 28 डिवाइडेड बाय 30. दिस मच fraction to be added to the knapsack. 28 divided by 30 and its profit is 120. Okay, so 4 and 4 112 and this will be what? 264. Now see the 264 and here 254. So this 264 is greater than 254. So simply we can move to the right branch here. Okay, so now just here again x y1 y2 equal to 1 y2 3 6 54. Okay, now y2 is 3 and y2 equal to 1, that is 10 and 80. Okay, then this is to be added. 4, 4 y3 equal to 1, 4, and 10 and 12 is 22, 22 and 22 and 72. Okay, sorry, 80 plus 72. 80 plus 72 is 2 and 152. Okay, 152. Now the fourth weight. Fourth weight cannot be added because 22 and 30. 22 cannot be added into 30. So simply just here the fifth weight is 0. Fourth weight is 0. Y equal to y4 equal to 0 and 4 and 22 and 152. But already just our solution vector is 254. So one vector is 0, 1, 1, 0. But its profit is 152 and which is less than the profit of the solution vector generated so far. So I will not override this x. Okay? So now here again we go for this y3 equal to 0. If y3 equal to 0, then the same is copied. No change in the weight and profit. And now the third weight. Third weight is excluded and then we take the decision for the fourth object. This is 10. So the fourth object can be added the fully, that 30. So here the fourth object is added, that is what fourth, and simply fifth and 40 and 200. Again this is less than that. So this another 0, 1, 0, y4 equal to 1. 0, 1, 0, 1. This is another solution vector. But we all these are leaf node. Okay. So here simply this cannot be added. Okay. Now y4 equal to 0. Come here. If we consider here y2 equal to 0. y2 equal to 0. Okay. So that's if we get the y2 equal to 0, then simply we get what? Here y2 equal to 0. See, y2 equal to 0, that is 3, 0, 0. y3 equal to y2. y2 equal to 1, y2 equal to 0. Again, see the next whether to move in this direction and we will get the better solution or not. So here just third and fourth object are remaining. Third object can be added. So its current profit is 72 and the current weight is 12. Okay? That is I is equal to 3. I equal to 4. The current weight will be 12 plus 30, that is 42, and the current profit is 120 plus 72, that is 192. 192 is less than 254, so we will not move to this branch. In this way the whole tree is explode. See, the whole tree is explode and only one solution vector is generated at the end, 1101, whose profit is 254. You draw this in this way that all the leaf nodes will be at the same level. In this diagram they are not at the same level. So this is okay, but here just 422, 152, just now see, this is the correct tree where all the just how many leaf nodes are 1, 2, 3, 4, and this node killed due to the bound function. This node is also killed. Okay, so now I will try, before giving the algorithm, to try to understand this and I will give here the problems. Only the complication is to determine the bounding function to move to the right branch for killing of the node. Okay, for that we relax the condition for k plus 1 to n and fractions are allowed, and then we compute the profit. If that profit is greater than the profit of the solution vector generated so far, then we move to the right branch, otherwise the node will be killed. So here some upper bound is used by relaxing the condition from 0, 1 to the fraction only for the objects k plus 1 to n. Okay, although I know that this is a difficult one, so before giving the algorithm in the next part I will try to explain this with one more example. Okay, thank you.